Hi, I'm Linka. This talk will cover material from a paper studying the messaging protocol of Telegram, which was joint work with Martin Albrecht, Kenny Patterson, and Igor Stepanos. Given the focus of this workshop, I will narrow it down and mainly talk about the attacks in the paper. So briefly, I will first motivate why we did this work and introduce the protocol in a less formal way. I will explain the attacks, both on the protocol and the implementation level. And to conclude, I will briefly mention what we learned from the proof side of the project. Telegram has grown in popularity in recent years, claiming to have reached 550 million users last year, but that's only a part of the picture. The thing that makes it especially interesting is that it gained a reputation for being a protest app around the world. It was used for coordinating protests in Hong Kong and Belarus, just to give two examples. In these protests, it was always described as an encrypted messenger on par with Signal or WhatsApp, even though they give very different security guarantees in practice. The cryptographic protocol securing Telegram is custom-made and does not follow standard practice. Yet it has not received much detailed study to date. 3 attacks were described in previous versions, 1 theoretical IND-CPA attack and 2 attacks on implementations. There is also a recent paper that proved Telegram to be secure in a symbolic setting. However, it abstracted away most of the details of the building blocks of the protocol. Further, most of the focus on Telegram has been on so-called secret chats, which are supposed to provide end-to-end encryption. However, they have very limited functionality and seem to not be used much in practice. So most users are actually using cloud chats, which only secure the client-server links, and these are the focus of our work. So MTProto version 2.0 runs directly over the transport, which is normally TCP or HTTP. Now, at a very high level, the key exchange uses a variant of the Diffie-Hellman key exchange, the output of which is a 2048-bit value, which is called an auth key. The symmetric channel could be described as a stateful encrypt and MAC construction using AES in IgE mode, which I will get to later, and the heavy use of SHA-256. This scheme has a few quirks, the most important one being that the client and server use different but related keys. And so the direction matters for how a message is encrypted. And this symmetric channel was the main focus of our work. I will now go through this in more detail. We start with the auth key and a plaintext payload. The entire auth key is first run through SHA-1 and truncated to compute something called an auth key ID, which just serves as an identifier for the connection. Next, a portion of the auth key is run through SHA-256 together with the payload. In the middle 128 bits form a so-called message key, which will also serve as a MAC. Then, a different portion of the auth key is used with the message key in 2 more SHA-256 calls, and then interleaved to produce a symmetric encryption key and IV. Finally, this key and IV are used to encrypt the payload using AES-256 in IgE mode. And so what is actually sent on the wire consists of the auth key ID, message key, and the ciphertext. There's a few things you can notice at this point. First, you see that this is an encrypted MAC construction because the message key is sent along with the ciphertext, and the receiver must decrypt first before checking the MAC. And the second thing is that the derived encryption key is message-specific, because as you see, it depends on the payload through the inclusion of the message key in the KDF. One thing I didn't show in detail in the first diagram was how the various slices are taken from the auth key, and you can see it here. So when the client encrypts a message, it uses keys that are mostly overlapping with the keys that the server uses, but not fully. And this is what the actual plaintext payload looks like. It has a header that is composed of 64-bit or 32-bit fields. And here the first 2 fields, server salt and session ID, are normally unchanged for the duration of a single session, where the server salt is generated by the server and the session ID is chosen by the client. The message ID here serves as an identifier for the particular plaintext, and it implicitly also includes a timestamp. The message sequence number is essentially just a counter of sent messages, and message length stores the byte length of message data. So here message data contains the actual request or response, which also has a specific format, but we do not model this and consider message data as our input message. And finally, this is followed by between 12 to 1024 bytes of random padding. To say a bit more about the IG mode, it stands for Infinite Garble Extension, and it was first described by Campbell in 1978. As you can see from the diagram, it's basically like CBC mode with the addition of also chaining the plaintext blocks. It was supposed to have infinite error propagation and therefore provide integrity, but this claim is actually not true, because one can modify a ciphertext in such a way that it will differ from the original only in 2 blocks. However, MTProto does not rely on this property, and because it has message-dependent keys, it is essentially only used as a one-time cipher. Before going over the attacks, I will quickly set the stage for what we actually looked at and what the implications of this are. First, to re-emphasize, we looked mainly at the symmetric channel part of the protocol for encrypting cloud chats. Implementation-wise, we looked at 3 official clients, and that is for Android, iOS, and desktop. Telegram also provides a cross-platform library that implements MTProto, however, the official clients don't make use of it. Further, the protocol implemented across these clients is roughly similar, but not entirely the same, especially when it comes to details of how the plaintext format is processed. And this also has implications for our attacks. Further, there is no clear separation between the code of the protocol and application code. But we had to make this cut for our analysis somewhere, so there is possibility we missed some problematic interactions. We also looked at the official documentation for MTProto, which was in some cases outdated or incomplete, so it also cannot serve as a definitive reference for the protocol. Finally, we inferred server behavior from practical experiments, since Telegram has expressed multiple times that they do not have any plans for publishing server code. All in all, this means that at least at the time of our study, it was not possible to have a single specification of this protocol, which had implications mainly for our modeling part of the work. I will now speak about the 2 simpler attacks that exploit payload validation. The first one is message reordering in the client-to-server direction, which is due to insufficient checks on the message ID and message sequence number, which are determined by the sending order of the messages. And this is because the server decides the final order of messages, not based on these values, but based on when it receives the messages. We confirmed this in practice on the Android client, and it's worth noting that despite what Telegram claims, this kind of reordering is easily preventable, and it's either on the MTProto level or the application level. The second attack is enabled by the re-encryption of unacknowledged messages. What this means is that most messages in Telegram require a special acknowledgement message to be sent back. If they don't get this acknowledgement within a given time, the messages are re-encrypted using the same message ID and fresh padding. In practice, this means that the stateful scheme is no longer stateful, because all of the plaintext headers are the same. So we describe an IND-CPA attack in the setting where the adversary controls the randomness, which is a strong assumption, but our proofs are also in this setting. And if the stateful scheme works properly, then the randomness should not be needed. However, if you don't give the adversary this power, then this attack requires around 2 to the 64 queries, because you will need a MAC collision to produce a message key that will be the same for 2 ciphertexts. So then it's just a theoretical attack. Now, our attacks and the implementation exploit timing side channels. First, we found an issue during the processing of a received ciphertext in various official clients. This was in the message length field, which has certain constraints on it, and these were checked before the MAC in the message queue was checked. In both cases, Telegram returned the same error, but if the message length check failed, it would return early. The actual timing difference was quite small, about 3 microseconds, which was tested with the end-to-end implementation. Depending on the client, this lets us recover between 8 to 32 bits of a 128-bit plaintext block. This attack is similar to existing plaintext recovery attacks on SSH, in that the idea is to move a target ciphertext block to a position where the underlying plaintext will be interpreted as a length field, and then use the resulting behavior to learn something about the target plaintext block. What complicates it slightly is IGE, so we need to construct valid ciphertext with our target somehow in the second block, which I will illustrate shortly. And for this to work, you also need to know 2 other plaintext blocks. Suppose we have a plaintext made up of 4 blocks that look like this. So the first 2 have the header, and the next 2 have some message that we are interested in recovering. They are encrypted with IGE, using a key and IV derived as shown earlier. The last plaintext block is our target, and we further assume that M1 and M3 are known. For the preceding message block, this is perhaps reasonable, but the header block less so, because the server salt and session ID are effectively secret random values. However, these values are the same for many ciphertexts in the same session. For now, assume we have both of these blocks. What the attacker can deliver to a client is then the following ciphertext, made up of the first ciphertext block unchanged, followed by a new block, which is the XOR of the target ciphertext block with the 2 known plaintext blocks. The client that decrypts this will compute the following, where substituting C* we get this, which recovers the underlying equation on the left. And so the client will get the target plaintext block XORed with 2 known ciphertext blocks. And if the attacker can now leak some information from the message length field, they can directly compute bits of the target plaintext block. The previous attack requires knowledge of the first 2 header fields. So this attack attempts to recover one of them, the server salt. The server salt is normally generated by the server and periodically sent to the client. But in the connection immediately after a key exchange, this is different. So initially, the server salt is derived from a secret nonce that is sent by the client during the key exchange. More precisely, the server salt is an XOR of a portion of a so-called new nonce and a server nonce, where the latter is actually sent in plain text. The new nonce is, however, encrypted using RSA on a custom padding format that looks like this. It starts with the SHA-1 of the data, then the actual data, and finally padding, where the data can be of variable length. And notice that the padding is not included in the checksum, so the server must parse this before checking, and there is a potential for several timing side channels depending on what is checked first. Telegram doesn't publish their server code, and we were only able to test what checks are made, not their order. However, the developers acknowledged the attack, but did not offer any details on the server implementation. But first, let me walk through the first 3 steps of the key exchange in more detail. Assume that the server has an RSA public key with modulus n prime and exponent e. The client knows this because it is shipped with the app. The client generates a random nonce and sends it over in the clear. The server does the same, but it also generates a number n that is 64 bits and actually a product of 2 primes, which is intended as some kind of proof of work mechanism. It sends this over in the clear alongside other information that is not relevant to this exposition. The client has to factor n, and then it generates a new nonce, which is supposed to stay secret, and encapsulates it in a string of this form. where enc represents just a deterministic encoding function for variable length integers, and header is a fixed 32-bit value. And so this data is encapsulated in the custom format I have already shown earlier, which includes a SHA-1 of the data without the padding. It does textbook RSA encryption over this and sends the ciphertext over. So at this point, there are many options depending on what happens on the server side, knowing that the server has to parse data before checking the hash. We confirmed that the server did check the header value, some bounds on the encoding, as well as the values of P and Q. We also confirmed that it did not check the provided value of n, for example. And however, we could not determine the order in which these checks were performed. For this attack, we will assume that the leakage is from the header check, but the paper also discusses other potential leakage patterns. And you can notice here that in the plaintext format, the attacker already knows all parts of the message M except for the new nonce, the hash, and the random padding. For this exposition, suppose the header check returns early. If the attacker submits a chosen value C prime in place of the target, it can learn if the 32 bits in the header position of the decryption of C prime match the header value, which provides our oracle. And we can use this oracle in a similar way to Blackenbacher's attack by choosing C prime to be SI to E times our target, whereas the SI values are chosen randomly. And the probability of a correct match here is then 1 over 2 to the 32. We can rephrase our goal as recovering H and N prime from a message M of this form, where H is the unknown hash of data, gamma encompasses all known information, such as the values of P and Q, N prime is the new nonce that we want to recover, and P is the unknown padding. And here we need to recover the value of H first, because it is necessary for recovering N prime, our actual target. And written another way, the plaintext M is of this form, where the values L, L prime, and gamma are known to the attacker. To recover the hash, we first have to find random SI values such that M prime, the decryption of our chosen ciphertext, has a header match as explained earlier, but also that SI is sufficiently small so that the parts of M prime determined by the new nonce N prime and padding P don't contribute to the header bits of M prime, and they can essentially be ignored in some sense. With this, you can construct the lattice for inequalities of the form shown on the slide, where sigma I is unknown and Ti is derived from known values. And so finding a shortest vector in this lattice recovers the target hash when the parameter mu is 6. So we need to find 6 SI values that fit our criteria. Next, to recover the new nonce, the process is similar. We first have to find random SI primes values such that, again, M prime has a header match. And SI prime is small enough to let us ignore the padding, but large enough that the part of M prime determined by the new nonce does contribute to the header bits of M prime, because this is the value we want to recover. And so with this, you can construct a lattice of a similar form, where sigma I prime is unknown and Ti prime is derived from known values, but this time also include the recovered hash H. And finding a shortest vector in this lattice recovers all but around 4 bits of N prime when the parameter mu prime is set to 9. Recovering the rest is simple, however, because we can use exhaustive search by just recomputing the hash and comparing it with H. Overall, this attack requires around 6 plus 9 times 2 to the 32 queries and a small amount of offline computation. Now I will show the remaining steps in the key exchange, but in less detail, only to see that recovering this new nonce value also actually gives you a man in the middle on the key exchange. Both the client and the server use these nonce to derive a key and IV for symmetric encryption, which is, for our purposes, just some function that uses SHA-1. This key and IV are used by the server with IgE mode to encrypt data of this form, which includes a Diffie-Hellman value g to the a. The server sends this over, and similarly, the client computes its secret and encrypts it in the same format with IgE with this data and sends it over. Both compute the auth key and additionally another hash value using SHA-1 that depends on both the new nonce and the computed auth key and send it over. So here you can see easily that if we can recover the new nonce, we can manipulate these ciphertexts at will. However, there is only a short time window of 10 minutes to execute the attack, because otherwise, afterwards the server forgets the exchange. In terms of disclosure, we disclosed the results of our analysis to the Telegram developers in April of last year, which they acknowledged in June, and we agreed to a public disclosure date in July, 90 days after the initial disclosure. They also awarded a bug bounty for the timing side channel and for the overall analysis. During this process, we were informed that they do not do security or bug fix releases, except for immediate post-release crash fixes. So the vulnerabilities we reported were supposedly addressed as part of regular updates. And the versions that include these fixes are shown on the slides. Before I conclude, I will briefly mention some points that came up during the proof side of this work. First, some attacks that we thought were obvious are not actually possible against Telegram. For example, like length extension attacks on SHA-256. These are prevented in multiple ways, either through fixed length inputs and truncated outputs, but also by the uniqueness of plaintext headers. Second, although we prove security of the MTProto channel, our results require assumptions on SHA-2, the block cipher underlying SHA-256, which are in some cases highly non-standard and not studied before. For example, it must behave as a PRF with partial key leakage or on fixed inputs. Thank you for listening. If you want to read more, you can check out the full paper at the link on the slide.